Hello, human biology. Hope you are doing well as we go on through the continuum of this pandemic of the coronavirus. This week we're going over chapter 14, nervous system, and this is one of a few videos that I will be making throughout this week and next week to help help you out as you go on through the notes of the nervous system. So the topic that we're going to be going over in this video is rest potential and action potential, the difference between the two, and how does a cell end up switching from one to the other. So as you can see on my drawing here, this is a representation of any cell in the human body. And so I have within the cell here a negative charge. All cells that are at rest have a negative charge inside of them. Why negative? Well, you have a few things inside of them that makes it negative. The major component that makes a cell negative is proteins. And so I'm going to put that down on here. Proteins. Okay? That's the major one. And I'm just going to put down A negative to represent anions that have a negative charge. And so cells have a lot of proteins inside of them. So that's going to give them an overall negative charge. I'm going to give it a number for you. So the number of this negative charge is negative 70. Negative 70 millivolts. Okay, so that is what we call the resting potential. So this cell right now is negative. So it's at rest. When we want to activate this cell, we want it to become positive. So you can see on here with the graph here that if it starts off at negative 70, the goal for the cell that is going to become active is a positive 30. So I'm going to show you on here how does the cell go from a negative to a positive charge inside. As of right now, it's all negative inside, but the positive is on the outside. It's on the outside here. So what makes it positive on the outside then? Well, outside of the cell you have a lot of salts. The most common salts out here is sodium, which I'm going to put down as an Na plus. It's a positive salt. And so you're going to have a lot of salt on the outside here. So again, all this sodium on the outside, protein on the inside of the cell that makes it negative. Sodium on the outside that makes it positive on the outside. And so if I look at the graph that I have right here, right now this cell is starting off right here at negative 70. But let's say something happens. Let's say a stimulus occurred. Now this stimulus can be any type of stimulus, like it could be touch, it could be sound, it could be smell, it could be light hitting your eye, anything like that. All about, we in the beginning of chapter 14 it talk all about different types of stimuli that our senses picks up, touch, taste, smell, vision, anything like that. And so any type of stimulus will come across and hit this cell. Okay, so this is the stimulus. And what occurs right at that site of stimulus is that it opens sodium channels. Sodium channels that are right across the whole membrane. And so I'm going to put those down on here just to remind you that you have sodium channels all across this whole membrane here. So here's a whole bunch of sodium channels that are mostly closed off. And they're mostly closed off unless something like a stimulus occurs. Now when a stimulus occurs, these sodium channels, they open at the site of the stimulus. And so after the stimulus, this sodium is going to start coming in. It's going to come into this cell. And when the sodium comes inside the cell, you're going to have a flip of charges. Okay, so a flip of charges. So now I'm going to have the positive charges inside the cell at this location. So I'm going to do a quick little switch around here. So positive, 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 and I'm going to have negatives about like this. Okay, so what we have there is a flip of charges. in that one location where the stimulus occurred. Now this change of charges here is what we call an action potential. Action potential. So this is where this region of a cell has become active. What will be the charge inside this cell now? It's not negative 70, it's positive 30. Positive 30, so now it has become positive 30 in just that region right there. Just that region. So if I show you by this graph down here again, we start off at negative 70, but then the stimulus occurred right here. And when the stimulus occurred, sodium channels open, sodium comes into the cell, making it become less negative. It actually is approaching 0, okay, on its way to becoming a positive charge. And so here, as more and more sodium goes in there, it's going to be getting closer and closer to 0. Now there's a point right here called a threshold, and I'm going to put that as a dotted line right here. The threshold. The threshold is usually about negative 50. So negative 50 millivolts. As soon as it hits that threshold, all these channels, all these sodium channels open up, and all that sodium rushes in, and it's going to shoot all the way up to positive 30. All the way up, just like that. Okay? So positive 30, and this is where the action potential truly is. This is where the cell becomes active. It's right at that peak of the action potential. Okay, so right here, right at the peak is, I'm going to put down AP, action potential, right up there. You may be familiar with this when you're looking at an EKG, because an EKG looks like this. Okay, you've probably seen that before, and you probably know, if you know anything about EKGs, is that this spike right here, this little peak, this is where the ventricles of the heart, boom, contract and become active. Outside of that, these are the part where the heart is actually relaxing to receive the blood. So right there, that spike, that's where it's, boom, is really contracting. And so here you have the cell has gone from resting to being active now. Right here, because the sodium went into the cell. That is a process that we call depolarization. Depolarization. And that is due to a sodium influx. Sodium going into the cell because the stimulus opened the channels and the sodium rushed in. Now after this action potential, the cell needs to go back down to resting again. So how is it going to go back down to resting again? How is it going to get back to negative charge? Well, the simple answer may be, well, can't you just kick sodium out? Well, no, you can't just kick sodium out. The reason why you can't kick sodium out is because sodium diffused into the cell. And when it diffused going into the cell, it's going from high to low. Okay? If for sodium to go back out, it's going to have to go against the gradient, low to high. That's going to require energy. That's not going to be easy to do at all. So sodium is out of the equation. Sodium is not going to leave the cell easily. And so you have to think about, well, is there something else within the cell that may have a positive charge to it? Now, we talk about proteins. They have a negative charge. A lot of times proteins don't leave the cell anyway, they stay within the cell. Sodium is out of the question because it's going against the gradient and going to use up a lot of energy. But there is one more salt inside the cell I have not talked about yet. That salt is called potassium. Potassium. Now, potassium is initially found inside the cell. Now notice potassium K has a positive charge in it, and it's just sitting there inside the cell, not doing anything right now. So by taking potassium out of the cell, right here, it's going to shift the positives back outside the cell, bringing the cell back to negative. And so when I show you that on this graph right here, when potassium leaves the cell, it's going to bring it back down to negative 70. This is called repolarization. To repolarize means that cell is working its way back down to being negative, and that happens by potassium efflux. Potassium leaving the cell brings it back down to negative 70. And so to review what I just covered here, sodium goes into the cell to activate the cell. And again, sodium goes into the cell because the stimulus opened up the channels and brought the sodium inside the cell. Potassium relaxes the cell. Now, why does potassium relax the cell? Because potassium leaves the cell, making the cell go back to being negative, going back to its resting potential of negative 70. So it's potassium leaving the cell that relaxes. I want you to remember that sodium stimulates, potassium relaxes. We talk about hypertension. The main cause of hypertension or high blood pressure is sodium. Sodium in a diet. So we actually link sodium to muscle spasms, speeding up heart, increased blood pressure. So sodium causes the cell to become active. Potassium has an opposite effect. You may know this because if you ever had a muscle cramp, you may think, well, the food I'm going to eat to relax that muscle cramp is bananas. Now, bananas is high in, guess what? Potassium. And so potassium relaxes. Potassium is going to bring that cell back down to negative 70. Right? But it does it by leaving the cell. That's called repolarization. Repolarization. Now the last step here, after the potassium leaves and that negative 70 is back to being seen inside the cell, there's one more change that needs to happen, because right now potassium is outside the cell, sodium is inside the cell still. That needs to switch around. Sodium needs to eventually go back out. Potassium needs to come back in. But that's going to be going against the gradient. So if it's going against the gradient, that means it's going to use energy. We talk about that with active transport. So the last thing that we need to do here is use active transport to put the sodium and potassium back on the correct sides of the cell. So we need to have something that's going to kick sodium out and bring potassium back in at the same time. Now this is something we discussed before. The name of these structures that do that is called sodium potassium pumps. Pumps. We talked about pumps. We talked about pumps with active transport. Active transport uses ATP to pump things against the gradient. Okay? And that is the last step there to make it go into full recovery, is that it goes through sodium potassium pumps. That pumps the sodium back out, pumps the potassium back in, and once it gets to that point, it's right back to square one again, and it's ready for that cell to fire back up whenever it gets that stimulus again. Okay? And all this happens in milliseconds, because the whole thing about the nervous system, it is extremely fast. Okay, it's extremely fast. When I talk about a millisecond is 1,000th of a second. This happens in just less than a millisecond. So less than a thousandth of a second. That stimulus has activated a cell. It activated a nerve. And in several milliseconds, that stimulus right here, this change that we call an action potential, doesn't just stay at the receptor. It moves all the way to your brain for your brain to process it. Okay? And that's what you learned in the beginning part of chapter 14, is that you have these receptors like in the fingertips that pick up that stimulus, that causes that action potential, that causes this switch of the charges, and then that disturbance moves. And it moves right along the whole nerve and goes all the way up to your brain. And your brain processes these little changes right here to determine what's the appropriate action to take. And we talk about that with homeostasis. Is it a good thing or is it a bad thing? How should we react to it? And once the brain processes what's appropriate decision to make it, or decision to make, it will send that signal to the effector organs, muscles or glands. So let's say in this case, it was your hand touching a surface, a hot surface, like maybe a stove surface. Hand touched it. The stimulus was a high temperature, and it caused the sodium channels to open, sodium rush into the cell, activating my receptors, my thermoreceptors that detect temperature on the outside of my hand here. And then it picked up the disturbance that those switch with charges, and it sent that disturbance all the way up to the brain. The brain processes it and said, ooh, that's not a good thing. Because if that hand stays there, the skin is going to burn, my flesh is going to burn, it's going to go down to muscle, to bone, it's going to be a really bad injury. So what's the appropriate response? Move that hand. Well, how does the brain move the hand? Well, the brain sends a signal to my muscles and tells the muscles, move that hand. And then the muscles, boom, respond and moves the hand. Again, this process does not occur and it does not take seconds. It takes milliseconds. It's not like if you press your hand on something hot, it just sits there like, oh, then it responds. No, it's a fast action. It's like something hot. Oh, I gotta move my hand off of that. Milliseconds. It is that fast. Okay? So, review the part of chapter 14 that talks about resting potential and action potential, depolarization, repolarization, and the role of sodium potassium pumps to reset it all. Okay? If you have any questions about this, email me or post your questions on the discussion board forums under the Q&A for the nervous system. I wish you much luck in studying, continuing studying chapter 14. I will post more videos on a couple more topics as you go along here. Okay? Just keep on communicating with me as you go on through this period of online courses. I wish you well. Take care. Wash hands. Stay away from people. Okay? Stay healthy. All right. Take care, everyone. Bye.